So let's continue with the semiconductor in equilibrium. In today's lecture, we'll be deriving the intrinsic carrier concentration, we'll be deriving the intrinsic carrier concentration n of I, and then we'll be analyzing the position of Fermi level E of F. But remember that these are all for an intrinsic semiconductor. Now, in the previous lecture, we had derived the thermal equilibrium electron concentration that is N naught and the expression was NC exponential minus EC minus EF upon KT, where NC is the effective density of states, and the expression was NC 2 into 2 pi mn star KT upon h square raised to the power 3 by 2, where mn star is obviously the effective mass. So if we evaluate the value of NC at the room temperature, that is at 300 Kelvin, and by assuming that the effective mass is equal to the rest mass, then the value of NC comes out to be 2.8 into 10 to the power of 19 per centimeter cube, and this is the value which holds true for most of the semiconductors. Alright, even in the last lecture, I have given you an idea of how to derive the thermal equilibrium hole concentration using again the integral formula. That is, it will be a product of the density of states in the valence band multiplied by the Fermi Dirac distribution for the holes, and its integral will be from minus infinity to EV. This part is left as an exercise for you people. So you will derive it, and the result will be similar to the one which we have derived for the electron concentration. So P naught will come out to be NV exponential minus EF minus EV upon KT. So this will be the expression which you people will derive it yourself, because the method is the same as we have used in deriving the thermal equilibrium electron concentration using the gamma function. So we'll do the same method of putting eta equal to some EF minus EV upon KT. So we'll proceed in a similar fashion for this as well. Alright, I guess eta should be if eta was EC minus E, eta was E minus EC by kT in the thermal equilibrium electron concentration, so here it should be EV minus E upon kT. Alright, so we'll proceed in the similar fashion, and for most of the semiconductors, P naught has a value of the order of 10 to the power of 19 per centimeter cube at a temperature of 300 kelvins. Yeah. So now coming to what we are going to derive today is, first we'll derive the intrinsic carrier concentration. Till now we have heard of the intrinsic carrier concentration as being the concentration of the carriers when the semiconductor is purely intrinsic. No external impurities are added to it. Alright, now how do we proceed on deriving the intrinsic carrier concentration? We know that the law of mass action states that under thermal equilibrium, the product of the concentration of electrons and holes is equal to the square of the intrinsic carrier concentration. So we know the expression for N naught, we know the expression for N naught, we know the expression for P naught. We can simply substitute it here and get Ni square. So let's just put the value of N naught. N naught is our NC exponential minus EC minus EF upon KT, and P naught is NV exponential minus EF minus EV upon KT equals to Ni square. So we'll separate NC and NV. When bases are same, powers will be added, so it will be exponential minus EC. Let's just open up the brackets now. Plus EF minus EF and plus EV upon KT equals to Ni square. This will be further NC NV exponent. Now see, here this EF and this EF will go, so it will be minus EC minus EV upon KT equals to Ni square. So Ni square equals to NC NV exponential minus EC minus EV upon KT. Alright, now what is EC minus EV? What is EC minus EV? That is the difference of the energies between the valence band and the conduction band. So if I draw something like this, if this is your EC, this is your EV, what is EC minus EV? EC minus EV will be your this gap, and this EC minus EV is simply our energy band gap. So Ni square will be equivalent to NC NV exponential minus Eg upon kT. So Ni would be under root of Nc Nb exponential minus Eg upon 2 kT. Alright? Yeah. Now, see, it seems from this expression that Ni is proportional to exponential of minus 1 upon t, because Eg is a constant, 2 is a constant, and k is a constant. So that means Ni varies exponentially, Ni decreases exponentially with temperature. Alright, but let us not forget that Nc and Nv are the effective mass, the effective density of the states in the conduction band and the valence band respectively, and they also contain a parameter which is the temperature, and Nc and Nv both are proportional to T to the power of 3 by 2. T to the power of 3 by 2. So we cannot ignore this variation of Ni as well, and then only we can get a clear picture. So that is, after substituting it there, this would be Ni is proportional to T to the power of 3 by 2 exponent of minus Eg upon 2 kT. Alright? Now, let's apply ln on both the sides to see how the intrinsic carrier concentration varies with the temperature. Yeah. So it would be ln of Ni proportional to ln of T to the power of 3 by 2 into minus Eg upon 2 kT. That would be ln of Ni proportional to 3 by 2 ln of T minus Eg upon 2 kT. So what do you think that among the two terms the variation of the Ni with the temperature will dominate? So obviously it would be the first term. So Ni is a strong function of temperature. So if we'll directly take it as, so Ni varies as T to the power of 3 by 2. That is, with the increase in the temperature, the intrinsic carrier concentration may become 3 to 4 times. Here shows the intrinsic carrier concentration versus the inverse of temperature and with the temperature here. So we can see that when the temperature is high, the intrinsic carrier concentration is at its maximum, and when it goes on decreasing, the intrinsic carrier concentration decreases. So we have 3 plots. You can easily find it out from the Google. If you search the keywords intrinsic carrier concentration versus the temperature, so you will find that with the inverse of the temperature, it becomes maximum when obviously the inverse is at the high value, because this is the value of the temperature. and if you take the temperature like this, so it will be maximum over here, and when the temperature decreases, the intrinsic carrier concentration also decreases. Alright, okay. And among these three, that is gallium arsenide, silicon and germanium, at a fixed temperature, the highest carrier concentration is found out to be in germanium. Yeah. Alright, now let's go to the, okay, and Ni has a value of 1.5 into 10 to the power of 10 per centimeter cube for the silicon. I guess this is the correct value. Yeah, it's 1.5 into 10 to the power of 10 per centimeter cube for the silicon, and has a value of 2.4 into 10 to the power of 13 per centimeter cube for germanium, and a value of 1.8 into 10 to the power of 6 per centimeter cube for the gallium arsenide, which was quite evident from the graph as well. Alright, and now now let's just try to mathematically analyze the position of Fermi level, that is E of F. Now since we are saying that this is an intrinsic semiconductor, so EF would be used as EFI, where I stands for the intrinsic. I stands for the intrinsic. Now, how do we proceed? We know that in an intrinsic semiconductor, the number of holes is equal to the number of electrons. So P naught is equivalent to N naught. Now substituting the expressions for P naught and N naught, that is the thermal equilibrium electron and hole concentration, we'll have Nc exponential minus Ec minus Ef upon kT equals to Nv exponent minus Ev minus EFI upon kT. I guess it's the reverse. Sorry. It is EFI minus EV upon kT, and this is EC minus EFI. Yeah. Now I am using it because I've already assumed that EF is equivalent to EFI. Till now we had only said that EFI or EF in an intrinsic semiconductor lies somewhere between the occupied bands and the empty bands, and in between the occupied bands and the empty bands is the forbidden gap. So we had assumed that the Fermi level in an intrinsic semiconductor lies in the forbidden gap, but where in the forbidden gap, that is what we need to see now. So we'll just try to mathematically transfer these equations, a bit of mathematical manipulation like this. We'll take the numerator on the left hand side to the right hand side. It will be V by NC, yeah, exponent minus EFI minus EV upon KT and then again some of the mathematical manipulation. Maybe we can take 1 here, NV by NC, NV by NC exponent minus EFI minus EV upon KT whole divided by exponent minus EC minus EFI upon KT. Alright, and then 1 equals to NV upon NC. Then the bases will be same, powers will be subtracted. It will be exponent of minus EFI minus EV. So the subtraction of this will lead to plus EC and minus EFI. So 1 would be NV NC exponent of and divided by KT, obviously. Yeah, how can I forget to write it? So it is minus 2 EFI minus EV minus EC. Let me put it like this. Alright, upon KT. Alright, now we are interested in finding out EFI. So let's just transfer it to take this term to here. It would be 1 upon exponent minus 2 EFI minus EV minus EC upon K into T equals to NV upon NC. Okay, so 1 upon this will be the exponential of minus this thing, so it would be exponent 2 EFI plus EV minus EC upon KT equals to NV upon NC. Yeah. Oh, I'm sorry, we do not have here minus EV, it's plus EV because it's minus EFI plus EV. So obviously it would be EV plus EC. Yeah, it would be EV plus EC, EV plus EC. Yep. So let's apply ln on both sides of equation. So what do we get? We get ln of NV upon NC equals to 2 EFI plus EV plus EC upon KT. So this would be KT ln of NV upon NC equals to 2 EFI plus EV plus EC. Yeah, and then E of Fi would be equal to EC plus EV upon 2 plus 1 upon 2 kT ln of Nv by Nc. Alright. Now, what is this Ec plus Ev upon 2? That is simply, if we have an intrinsic semiconductor and this term, this level is Ev, this is Ec, so Ec plus Ev, that means adding these two energies and dividing it by 2 is going to give you a energy level which lies in the middle of the band gap. So EFI will be E of mid gap plus 1/2 of kT ln of Nv upon Nc. Okay, now EFI equals to E of mid gap when if temperature is equivalent to 0. So this is the fact that at T equals to 0 Kelvin, intrinsic Fermi level lies in the middle of band gap. Alright, so our assumption that the Fermi level in an intrinsic semiconductor lies in the middle of the band gap now has been proved analytically true. Now if we further want to see for a finite temperature the variation of EFI with the temperature, we can simply substitute Nv by Mp star and Mn star raised to the power 3 by 2, where all of the terms cancel out because of being the equal value. So it is E of mid gap plus ln of M raised to the power N, it's 3 by 4 kT ln of Mp star upon Mn star. Now here another condition arises, that is if the effective mass of hole is equal to the effective mass of electron, then in this condition the second term would be ln of 1, which is 0. So second term becomes 0. And what is our E of Fi? Our E of Fi is again in the mid gap. Now another condition is if Mp star, that is effective mass of hole, is greater than the effective mass of electron, then the term on the right hand side would be greater as compared to the EFI, isn't it? That means this term would be greater than this. So E of Fi will be above center. Alright, now if Mp star is less than Mn star, so the right hand side is lesser than EFI, so the position of the intrinsic Fermi level will be below the center. This is how the intrinsic Fermi level varies with the effective mass. Now effective mass is in itself a function of the effective density of states, or simply the density of states. Therefore, The intrinsic Fermi level must shift away from the band with the larger density of states in order to maintain equal number of electrons and holes. I hope this lecture would be useful to you. With this, the analysis of the intrinsic semiconductor is complete, and if you have any queries related to this, you may write back to me.